Welcome back to CMOS RF integrated circuits. As part of module 6, that is wideband amplifier design, that is what we were doing. Today we are going to discuss the shunt series amplifier. In the past we have studied, we have basically modified the load, put an inductor over there, basically created a 0 and a pair of conjugate pole pairs, and have tried improving the bandwidth. We came up with, I basically told you that 3 inductors put together will work even better than the one inductor, than the solo inductor. That particular circuit is called that the set of 3 inductors is the T coil. So, that is also used a lot of times, and then today we are going to discuss the shunt series amplifier. Now, the shunt series amplifier is basically you have got source degeneration as well as something across the gate and drain. So, in the past I called that R2 and the bottom one R1. So, that is fine. Now, this is basically my plan, and what do you think about this? We want to first find out the low frequency gain, then we want to estimate the bandwidth. Right? These are the two things that we have to do. Now, low frequency gain we are going to find out in a moment, but before that I just want to say something about the bandwidth. How are we going to find out the bandwidth of this circuit? Can we use the method of open circuit time constants? Yes, we can. We can use the method of open circuit time constants, there is no problem. Why? Because there are no inductors. Because there are no inductors, there is most probably not going to be pair of complex conjugate poles. Also, I am going to assume that there are no zeros, there is going to be a 0. I am going to assume that there are no zeros. So, that will give me an estimated bandwidth, right. So, this is basically the idea, fine. So, I can definitely use the method of OC time constants to find out the bandwidth. I know how to use it, what to do with it. Okay. So, before that let me try to find out the low frequency gain. How do you find out the gain of a circuit? You use the Norton equivalent model, right. You want to model your circuit, this is my circuit, as a current source in shunt with an output resistance. So, if I can model this as this, Norton current source and an output resistance, then I can find out the gain very easily, right. The gain is IN, output voltage is IN times R out in parallel with RL, fine. So, to find the gain what we do is to find the Norton equivalent current we use the what experiment? What experiment do we do to find out the Norton equivalent current? We do the short circuit experiment. We short the output to ground and see how much current is flowing here. That will tell me what is the value of IN. If you do it here, then IN will go through the short circuit. So, that is why short circuit experiment, right, just a reminder. So, we are going to do the short circuit experiment. So, as soon as I do the short circuit experiment, I can throw out RL Okay. If there is any capacitor at the output, some lumped capacitor to ground, that also gets thrown out, etc., etc. MOSFET is going to be replaced by a GM and an RDS. Okay. If you also want to incorporate the body effect, then it is effectively going to be GM plus GMB. Fine. Okay. So, this is my situation. All right. So, let us say that the voltage at this point is V1, the voltage at this point is V2, okay, and then I have got to write out two Kirchhoff's equations, Kirchhoff's current equations. So, I have got V minus V1 by Rs, that is the current over here, that should be equal to V1 minus 0 by R2. Right. So, what is V1? Fine, in terms of V. So, in terms of V I already know what is V1. Okay. Now, we need to do a second Kirchhoff's equation for the node V2. So, for V2 what I have got is as follows: V2 by R1, that is the current going downwards, V2 by RDS is the current going through RDS, and that should be equal to GM times VGS. What is VGS? VGS is V1 minus V2. Fine. So, basically you collect all the terms with V2. When you collect all the terms with V2, this is what you get. Right. So, these are my two node voltages, but am I interested in the node voltages? Not really. What I am interested in are all the what I am interested in are the short circuit current, right. So, the short circuit current is going to be how much? it's going to be V1 by R2 that current is going to go through the short circuit, right. The current through V2 by R1 also is going to come from the short circuit, it's coming from the short circuit, coming out of the short circuit, right. So, this is what I am really interested in. So, V1 by R2 is V by Rs plus R2, that is one thing sorted out, and V2 by R1 is this particular quantity, and therefore, what I have really got I n is equal to V by Rs plus R2 times 1 minus this is what I have got. All right. Do you agree? So, that is your Norton equivalent current. Fine, that is experiment number 1 done. Experiment number 2 is the output impedance. So, this experiment I am yet to do. All right. So, what we are going to do over here is as follows. We are going to replace the MOSFET by GM and RDS. And to find the output impedance, you have to kill the input voltage, null the input voltage. All right, so far so good. So, if this is the case and you have applied a voltage V over here, you want to find out what is the current, right. So, first of all there is going to be a current through this pathway, and how much is that current? That current is V by R2 plus Rs. So, just keep this in mind, V by R2 plus Rs is already established in that pathway, and as a result of that the voltage at this particular node is Rs by Rs plus R2 times V. It is a voltage divider. Okay. So, this current has already been established. All right. Then what is going to happen to this particular node? Let us say that this node has a voltage Vx, right. I do not exactly know what is the value of Vx. So, let me write the Kirchhoff's node equation for that particular node Vx. So, Vx by R1, that is the current going downwards, that is equal to V minus Vx by Rds plus Gm times Vgs, where Vgs is equal to this quantity. And then once again I collect all the Vx terms together. So, when you collect all the Vx terms together, this is what you are left with. fine. So, what does that mean? First of all, what is my net current? My net current is the current through this old pathway plus the current through R1, because this eventually has to come from here, right. So, my net current is this. Okay. And that is one of the currents, and the other current I have got is this particular quantity. Now, what are we going to do? What is the impedance that you see? Impedance is V by I, which basically means that I need to do a little bit more of simplification, otherwise it is not really tenable. Which means that my output resistance is the inverse of this complicated quantity. Now, whenever you do something like this, where you can make mistakes very easily, you should always do sanity checks. So, what is a sanity check over here? First of all, what happens? First of all, you look at the dimensions. What are the dimensions of the numerator? So, in the numerator, the first piece over here should have dimensions of unity. So, dimensions are unity in all the three terms, fine. Second term has dimensions of resistance, fine. So, the numerator has dimensions of resistance, denominator should have dimensions of unity, because the net result should be a dimension of resistance. So, check, does the denominator have dimension of unity? Unity, 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 no dimensions, right. So, this is a first cut check to see if your result was indeed correct. Earlier what we had done, not an equivalent current, it is a current, okay. The dimensions should be in amperes. So, I have got volts over here divided by resistance. So, I have got amperes over there. Inside the brackets I should have no dimensions. So, I have got 1, which is good. Then numerator is no dimensions, denominator is also no dimensions. So, all is well. Okay. This is a first cut check to whether your expression is correct or not. If you make a mistake here, then that is it. You again rewind and work it backwards. Next sanity check would be to see what happens when R1 is equal to 0. What should happen when R1 equal to 0? Or let's suppose R1 is equal to 0, R2 is infinitely large and Rs is equal to 0. If R1 is equal to 0, R2 is infinitely large, then the output resistance should be equal to RDS. R1 equal to 0, R2 is infinitely large. So, this is 0, 0, R2 is infinitely large. So, the numerator is infinitely large. Denominator 1 plus 0, 0, GM times RS plus R2 plus RS by RDS. So, that is approximately equal to R2 by RDS. So, you have got R2 by RDS in the denominator and you have got R2 in the numerator. So, your net is equal to RDS. Okay. So, this is another check. Third check would be, let us say R2 is infinitely large. Let us have R1, no problem. Let us say R2 is infinitely large. Then my system boils down to, it should have a resistance of RDS plus R1 plus GM RDS R1. This is my formula. Remember the formula, right? Yeah. So, supposing R2 is infinitely large, does it boil down to this formula? Let us check. R2 is infinitely large. So, R2 plus RS is approximately R2. Again R2 is infinitely large. So, the entire denominator is basically going to be R2 by RDS. So, my denominator is R2 by RDS, numerator is R2 times 1 plus R1 by RDS plus GM R1. Okay. So, R2 and R2 cancel out with each other. 1 by RDS really is times RDS, and as a result you get RDS plus R1 plus GM RDS R1, which is your formula, right. So, these are all sanity checks that you can perform. What happens when R2 is 0? What happens when R2 is 0? What happens when R2 is 0, R1 is also 0? I should see RS in shunt with 1 over GM, in shunt with RDS, right. So, you do all these sanity checks just to, you do not need to do all of them, you can do a couple and double check, make certain for yourself that what you have done is indeed correct. So, these sanity checks are usually very helpful when you do complicated algebraic, you solve complicated algebraic equations. All right. So, this is my R out and this is my Norton equivalent current. So, therefore, the voltage at the output, you convert the Norton equivalent current to a Thevenin equivalent voltage, right. Let us say RL is infinitely large, let us not bother about RL. So, if you do not bother about RL, then you just multiply IN and R out and that is your voltage at the output, divide by V, that will give you the gain. So, therefore, the gain over here is IN times R out divided by V, right. So, RS plus R2 cancels out, 1 plus this complicated term cancels out. Okay. All you are left with are these two terms. So, this is the net gain of the circuit. Okay. Now, let us do a couple of approximations. Let us say that RDS is very large, that is my first approximation. So, if RDS is very large, then what we are going to get is the following. Okay. And then the second approximation that I am going to make is that GM is also very large, in which case 1 is small compared to GM times something, which means you can really ignore the 1 and GM will cancel out with the GM. So, you will basically get R1 minus R2 divided by R1 plus RS. This is the gain of the circuit. All right. Now, is this something you like? First of all, do you want gain to be more than 1 or less than 1? Do you want gain to be positive or negative? You want gain, the magnitude of gain, to be more than 1, right. You do not mind if the gain is negative. In fact, if you have a single transistor something, then you expect the gain to be negative. You are looking at the voltage at the drain, you expect the gain to be negative, you do not expect it to be positive. Okay. So, now we are talking. So, in that case, what is this? What is the story over here? Should R2 be larger than R1? R2 smaller than R1? You want the gain to be negative and you want it to be more than 1. So, R2 has got to be much larger than R1, right. Not only larger than R1, R2 has got to be R1 minus R2, I am sorry, R2 minus R1 has to be more than R1 plus RS. To give you any decent gain more than 1, which means that R2 has got to be more than twice R1 plus RS to give you any gain which is more than 1. All right. So, now that we have some idea of what is going on over here, we have some idea. We have, this is an accurate expression at low frequencies. It has GM in it, it has RDS. So, even for non-ideal MOSFET model, a good decent MOSFET model at low frequency, you can work it out. If you want to incorporate body effect, all you have to do is substitute GM by GM plus GM body, right. Remember to do that. And you have got a very accurate low frequency equation, description of the circuit. The next thing is, what about an approximate idea of what is going on? Approximate idea is when GM is large, when RDS is large, and when that is the situation, then what I have got is a gain which is approximately equal to R1 minus R2 by R1 plus RS. Let us take a few numbers and see for ourselves how approximate this approximate business is. So, let us say R1 is 1 kilo ohm, R2 is RS is also 1 kilo ohm, R2 has got to be more than 3 kilo ohms, let us say R2 is 10 kilo ohms, and let us say GM is 10 millisiemens, RDS is 2 kilo ohms. Okay. So, let us say these are the numbers that we are talking about. So, in that case, the approximate result gives me R1 minus R2, that is minus 9 divided by R1 plus RS 2. So, I get about minus 4.5 gain, which is not bad, about 12-13 dB, right. Okay. But if I plug in the numbers of GM, RDS, etc., I get 1 plus R1 by RDS is about half, GM times R1 is 10 minus GM times R2, that is 100, divided by 1 plus R1 by RDS is 0.5 plus GM times R1 is 10 plus GM times RS is another 10 plus R2 plus RS. R2 is 10 kilo ohms, RS is 1 kilo ohms. So, I have got 11 kilo ohms divided by RDS. So, 11 kilo ohms by 2 kilo ohms is about 5.5. So, what I have got over here is 1.5, 11.5 minus 100. So, about minus 88.5 in the numerator, and in the denominator I have got 27. Okay. So, I have got a gain which is 88.5 divided by 27, that is about 3.3. Okay. So, I have got lesser gain, but ballpark I get a feeling for what the numbers are going to look like. So, instead of RDS as 2K, if I had chosen RDS as 20K, right, suppose RDS was 20K, then what you would have got is 0.05 over here, 0.05 and 0.55, okay, and that would mean something like this. which leads to a gain which is more closer to 4.5. Right. So, you can do these you can play a little bit over there. Okay. So, this is what we have got. So, this is our shunt series amplifier. We can get gains out of this by choosing appropriate values of R2 and R1 etc., and in relation to RS, but of course. And now the next question is, what is its bandwidth? And to work out the bandwidth, what we have to do is we have to employ the method of open circuit time constants. Oh, I did not even consider a load RL. You basically have to put RL in shunt with whatever output resistance you have got, or what you can do is you can split the gain that you have got over your R out and your RL, and you can find out the net gain. That is also fine. So, for now I earlier assumed that RL is very, very large. You need not make that assumption. Fine. Let us pick up some sample numbers. Let us stick to the numbers that we have got, right. R1 1K, let us stick to these numbers. All right, and GM is 10 millisiemens, RDS is 2 kilo ohms. Let us also pick some numbers we had used earlier. CGS is 200 femtofarad, CGD is 50 femtofarad, C drain to body is 100 femtofarad, and C source to body is 150 femtofarad. These were numbers that we were using before as well. GMB is 1 more millisiemens. Okay. So, really you should be plugging in GM plus GMB over here, does not matter, right. And then we are going to play with the method of open circuit time constants. So, to do that we need to identify all the capacitors that we have got. The capacitors that we have got are these. I could not label C gate to drain. Okay. These are all the capacitors. Let us say that RL and CL, what do you want to put RL and CL as? What do you want RL and CL to be? Let us say RL and CL are 10 kilo ohm and 1 picofarad. All right, just some numbers over here. What would happen to R out? What is R out over here with my numbers? R1 is 1K, R2 is 10K. So R out would be 1 plus R1 by RDS is about 0.5 plus GM times R1 is factor of 10 times GM was 10 millisiemens, R1 was 1 kilo ohm, R2 plus RS is 11K. Yeah, this whole thing is to be divided by 1 plus R1 by RDS is 0.5 plus GM times R1 is 10, GM times RS is also 10, and R2 plus RS by RDS is a factor of 5.5. R2 is 10 kilo ohms, RS is 1 kilo ohm, so 11 kilo ohm by 2 kilo ohm, that is 5.5. So, I have got my denominator as 27, right. So, 11.5 times 11K divided by 27, how much is this? How much do you think it is? It is about 5K, little less than 5 kilo ohms. Okay. Do not want to do the full mathematics, it is about 4.8 K. Let us put a round number 5K. Now, I am trying to drive a load which is 10K. Okay, my output looks like a voltage source at DC. It looks like a voltage source of value about 3.3 times V input. So, that means that 2/3 of 3.3 is actually going to be transferred to the output, which means that my net gain is actually only going to be about 2.2 times the input. Net output voltage is only 2.2 times the input. All right, minus. So, keep this in mind. Right, please keep that in mind. Let's now proceed with the method of open circuit time constants. Okay. So, let's do them one by one. Let's first start with CL. When I talk about CL, the resistance that CL is going to see is 10 kilo ohms in shunt with the output resistance of the whole thing, which was about 5 kilo ohms. Remember? So, RL is really something like 3.3 kilo ohms. All right. So, net what I get over here is 1 pico, the time constant I get for the load capacitor is 1 pico farads times 3.3 kilo ohms, that is about 3.3 nanoseconds. Now, obviously, this is huge, right, and with this kind of a design you are not going to get anywhere, all right. This kind of a design you are not going to get anywhere. So, what you really have to do is you have to use a bigger transistor, smaller resistors all over the place, so that the output resistance of your circuit is much lesser. So, if I choose 10 times larger devices, 10 times larger conductances, then presumably I will get better numbers for the load capacitance, a better tau L, right. So, that is a design point that you have to do. So, instead of choosing RL so much, I am sorry, instead of choosing R1 as 1 kilo ohm, R2 as 10 kilo ohm, why didn't you choose R1 as 100 ohms, R2 as 1 kilo ohm, RS as 100 ohms, right. So, this and GM, why don't you choose it as 100 millisiemens and 200, I am sorry, 2 kilo ohms RDS. So, we could have done that. Fine, let us proceed with what we have got. What about CDB? CDB also sees the same resistance. CDB is about 100 femtofarad, so I do not see that much. All right. So, I have got 2 capacitors out of the way. Next, C source to body. What is the resistance that you see looking in upwards into the source of the MOSFET? Looking downwards, you see R1. Looking upwards, what do you see? First of all, what is my circuit? My circuit is like this. That is my circuit over there. Okay. What do you think you are going to see? You are going to see a small resistance, large resistance. First of all, whenever you look into the source, you see a small resistance. Okay. So, if you see kilo ohms, it is most probably not right. If you see hundreds of ohms, maybe you have done a good job in the computation. Okay. So, let us try. Something like this is what we have got, and of course, you replace the MOSFET with GM and RDS. Okay. So, you have applied V at the source, okay, and you want to find out what is the current going into the source? That is the question. So, suppose the current going into the source is I. So, what is the current coming out of the drain? It is still going to be I. All right. Now, this I is going to split into two parts. One side is going to the gate, towards the gate. One side is going to go into the load. One side is going to go towards the source, the other going to go towards the load. What fraction will go towards the source? Towards the source, you see more resistance than the drain towards the load. So, you will see less current, right. So, 10 by 21 times the current I will go towards the source. Agreed? Now, this is 10 by 21 I coming, and what is the drop across 1 kilo ohm? This times 1 kilo ohm is the voltage that is on the gate. All right. Okay. So, what is VGS? VGS is VG minus V. So, the next question is what is V? So, the current through the GM is GM times VG minus V, right, and that current plus I is the current through RDS. And what is the current through RDS? The current through RDS is the voltage at the output node, the voltage over here, minus, I am sorry, V minus the voltage at the output node divided by 2K. And the voltage at the output node is 10 by 21 I times 11K, that is the voltage at the output node divided by 2K. So, I have basically done a Kirchhoff's node equation at this particular point, right, and that is going to give me what is the relationship between I and V. So, then I put all the V terms together, all the I terms together. Vg really is something which is proportional to I. So, Gm times GM is really 10 millisiemens times 1 K, 10 millisiemens times 1 kilo ohms times 10 by 21 I. So 10 millisiemens times 1 K is a factor of 10. So I've got 100 by 21 I minus GM times V. And then I've got I over here, and I've got 55 by 21 I over here, and I've got half a millisiemens times V on the other side, right? So that basically tells me that I times 155 and 21 is 176 by 21. Hope I'm doing my arithmetic correctly. Okay. So the voltage that you've got is something like this. Which means that the resistance that you see looking in at that particular node is this quantity. Okay, 176 by 21 is about 8.5, no, a little less than 8.5, let's say 8.3 or so, and milli in the denominator means K in the numerator. So 8.3 kilo ohms divided by 10 and a half, it's about 800 ohms. Okay. So we said that we'll see a low impedance. We have got a low impedance. So we are going to stop over here. Oh, R1 we have to put in parallel. So 1K in shunt with 800 ohms, whatever that is, that's going to be about 600 ohms or so. And 600 ohms, 150 femtofarads, probably give me 30 picoseconds. No, 90 picoseconds. All right, so we are going to stop here. We have got a couple of more capacitors to work on. Actually, those are the two important ones, and we are going to wrap it up after that. So far we have been discussing the shunt series amplifier, and we'll see its benefits shortly. Okay, thank you.